for a little bit, I'm going to talk about multispectral dip and azimuth. You've probably heard me talk about multispectral quite a few times. You could run it on pretty much any of your geometric attributes, and it will give you much clearer images if you're having problems. So to explain what it is, here we've got an example of a time slice and a coherence volume. So on the grayscale on the left-hand side, you can see the faults. You can see regions where the fault is clear, and you can see regions where there is a gap in the fault, so coherence is not picking it up. The way we would handle this, particularly if we're very confident that the fault should be continuing on, is we kind of want to figure out, okay, what can we do to clean it up? Well, the answer is obviously look at the broadband data and specific frequency ranges. So do a multispectral analysis. So here we've got an example of some full bandwidth data with some faults in it, and you can see below the coherence. And so we've got some gaps in there. We don't like those gaps. We want to get rid of those gaps. So we can look at the spectral voice around 36 hertz. So breaking that out of the full bandwidth of your data. And here we've got much cleaner images. You can see that those faults are showing up much more clearly in coherence. Looking at it at 55 hertz, again, nice, clear, strong coherence signals. So hopefully that convinced you that there is a lot of value in taking the time to break out certain frequencies, to get better data, better results with your geometric attributes. And so just to show you one example, since I'm talking about dip, here's an example with dip magnitude. And on the left-hand side, we have the broadband results, and on the right-hand side, we have the multispectral results. And so you can very hopefully clearly see some of the differences in the fault expression, particularly on the lower portion of the image, where these faults are much more clearly defined. Thanks.